Welcome to EDU World Space.
We have two objects, a sphere and a ring, and on a line that's perpendicular to the center of the ring, we have the sphere. And then we're given the radiuses of each and their masses. And so we want to find the force, the gravitational force that the sphere exerts on the ring. So one trick we can use to start with this is that it's going to be a little bit tough to set this up. For doing the force the sphere exerts in the ring. And just because of the spherical symmetry of the sphere, we'll have to use spherical coordinates, which will just get a little bit involved. So from Newton's third law, though, we know that the force the sphere exerts in the ring has to be equal and opposite to the force the ring exerts on the sphere. So to simplify things, we'll instead think about the ring acting on the sphere. And then when we find that force, we'll just take the one in the opposite direction and say that's the force the sphere exerts on the ring. So we know that our gravitational force should be, just most generally would be g m little m r squared. And this would be in the r hat direction. But the problem is when we're looking at m here, all the little different pieces of m will have a different r hat. So we can't really use this equation. Instead, we need to set it up as an integral. So g little m, and then we'll say dm. So we're taking a little differential piece of the ring and just looking at the force that that makes. And then we're kind of going to add up all those essentially. So we have dm, and then in the r hat direction. And the nice thing about how this is set up now and looking at it from the ring's perspective is that all of these distances are going to be the same. So we're also able to reduce the sphere just to acting as a single point here in the middle. So we'll be doing that. So we're going to treat the sphere as just a single point in the middle with mass little m. And so now every part of this ring is the same distance away. And we can see, especially at this plane, that that's going to be, if this is distance x, and then this is a, we're making a right triangle. So the hypotenuse will be square root of a squared plus x squared. So that's always going to be r for this equation. So we have square root of a squared plus x squared, and that will be squared. So now we still have the problem, though, of the r hat, the direction the force is acting in, and those look like they're going to be all in different directions. So this piece is pulling it like that. This piece up here is pulling it like that. But we can see from symmetry pretty clearly that the net force is just going to be along the x-axis, or in this direction along the dashed red line. So every little piece will be pulling like up and down a little bit, but that all cancels out. So that tells us that for this particular case, that the net force is the same just as the force in the x direction. So we can then just think about the x direction here rather than in the full like r hat direction. So now we want to say, instead we'll think about fx, which is really the same thing. And we have g little m dm still. And then when we square this, we lose the square root. So just a squared plus x squared. And so now what's the x direction going to be? So for any given little dm piece of mass, we want to take just the x component of the force. So that will be just the part along this red line. So if we say this is theta, then to get this part, we would take sine of theta, so opposite over hypotenuse. Well, the opposite is length x, and the hypotenuse is length a squared plus x squared. So that'll give us the magnitude in the x direction, and then finally we say it is now in the x direction. So now we have our integral set up, and we can just integrate dm and get capital M, since none of these other things now depend on it. So when we integrate this, we should just get g little m, and then integrating dm, we just get capital M. And now all of our x's and a's, we should have x, and then a squared plus x squared times square root of a squared plus x squared should give us a squared plus x squared to the 3/2. And this is all, remember, in the x hat direction. So this will be the force that the ring exerts on the sphere. And so this would be in the negative direction we'd want to add in. So there'd be like a negative sign here. But if we want the sphere acting on the ring, then that'll be in the positive direction. And so we can just leave off the negative sign. And so this then will just be our answer. We're asked then to show that when x is very large compared to a, so the distance separating the two is much larger than the radius of the ring, that this reduces to the expected result, which is usually just where we treat each point as just a point particle. So if a becomes small, then, or rather if x is much, much bigger than a, then we say our force now is g little m big M x over, and now we basically get to ignore this a squared here since the x squared is so much larger. So we just have x squared to the 3/2 still in the x direction. So x squared to the 3/2 is just x squared, or x cubed. And so we cancel that x up top, and so we'll just get g little m big M over x squared in the x direction. So exactly the force we would expect between just 2 point particles that are a distance x away.